Hey, I'm Don with Block Harbor Cybersecurity, and this video is going to be about Unified Diagnostic Service. UDS is a very deep rabbit hole, and we can't cover its steps today, but we're excited to bring you a series on UDS, so stick with us, and hopefully you can learn something. A standard CAN packet can only transmit 8 bytes of data at a time. UDS will frequently need more than 8 bytes for things as simple as transmitting a VIN number. The UDS is powered by a protocol known as isotp. This isotp is defined in the spec ISO 15765-2. And these isotp packets, which will be called frames, are broken up into 2 major sections. The first section is the protocol control information. This tells the ECU what data is about to come, how much of it, and if there are multiple packets and frames coming. The second part, the protocol data unit, contains all the data that the isotp packet is trying to transmit. There are 4 types of isotp message, indicated by the first 4 bits of the first byte. The 4 types are single, first, continuous, and flow control. If this first nibble is a 0, that means that the entire isotp message, or UDS message, will fit into one single CAN frame. Many ECUs implement a UDS server, which handles requests on one ID and responds to them on another. In many cases, this can be predictable, such as in Ford vehicles where the response ID is 8 more than the request ID. In other vehicles where you can't predict this, you can look for an expected response. For example, if you're sending a 3E request, you can look for a response of 7E to find out what ID is responding to your message. The UDS spec defines many services an ECU can use. If you've ever read the codes off of Modern Car, you've already used 0x19 to read the diagnostic trouble code information. Some other codes include 0x11 for an ECU reset, 22 to read data by identifier, or 31 for routine control. You can find the full list of these codes in the Wikipedia link in the description, and we'll also go into more of them in part 2 of this video. Let's take a look at a UDS request. The first thing is the arbitration ID. Here, it's 7E0. Then, the first nibble of the protocol control information field is a 0, indicating that this isotp frame is only a single packet. The second nibble is a 1, indicating that the amount of data transmitted is only going to be 1 byte. In that byte, the first byte of the data field is a 3E. That first byte is the service identifier, and there's no more information to transmit in this packet. Now that we know what an isotp message looks like and what a UDS server is, let's take a look at an example communication between an application plugged into the vehicle's OBD2 port and the powertrain control module. In this case, we'll be using the service identifier 3E for test or present. This is used to keep an ECU in a specific state while it's under test. In our Ford Mustang Mach-E, the powertrain control unit is listening for UDS requests on ARB ID 7E0 and replying to them on 7E8. The tester present uses the service 3E, and a success response will be found on 7E, which is the service ID plus hex 40. Normally, this would be followed by some more data in the UDS reply, but since we're just using a tester present, this is a success message. In the case where a UDS request fails, the server will respond with a 3-byte error. The first of the 3 bytes will always be a 7F. This indicates the failure. The second will be the service identifier that it received, and the third will be the error code, which can be very helpful in diagnosing why your UDS requests aren't working. Now, let's take a look at this example and figure out what went wrong. We sent a request at 7E0, received a response at 7E8 that is a single frame, 3 bytes long, but an error. That error happened when we got a message on service identifier 80, and our error code is 11 saying service not supported. Unlike with messages shorter than 8 bytes, messages that are too long to fit within one CAN packet will use what's called first and consecutive frames. These first frames will begin with a 1 in the first nibble to indicate that they are the first frame in a sequence, and all consecutive frames will begin with a 2 in the first nibble, indicating that they are follow-ons to the first. These consecutive frames will also contain a sequence number to make sure they get received sequentially and not interpreted out of order. The final type of ISOTP message is a flow control. This is broken down into 3 major parts. Aside from the 3 in the first nibble indicating that it's flow control, first you have the flow status. This flow status tells the sender how it should be sending all of the sequential messages. A 0 will indicate that the sender should continue to send messages, a 1 will tell the sender to wait, and a 2 will tell the sender to abort sending entirely. The other two parts are block size, which says how many packets to send at one time, and the separation time, which is how long should the sender delay between packets. Let's take a look at an example. Here, we're going to send an 18-byte message, which is far more than the 8 bytes we're allowed to use in a single CAN frame, so we need to use multi-frame messaging. You can see this by looking at the 1 in the first nibble, which indicates that this is the first of a many-frame continuous sequence. Because this is a many-frame message, our data length code is extended to be 12 bytes from the second to the fourth nibble, which you can see here in hex 012, which in decimal is 18, specifying 18 bytes. Now, the next byte is going to be 27, our service identifier for security unlock. Now, we're not going to go into security unlock in this video, but we will cover it in a follow-up video. We will finish filling out the rest of the 8 bytes in the first message, and then we'll wait for a response from 708. This response is a flow control specified by the first nibble being a 3. The second nibble being a 0 means to continue sending all of our messages, and the next 4 nibbles all being 0 indicate to send all of the blocks all at once. Once we get that OK for the flow control, we will again send another message, this time specified with a 2 as the first nibble, meaning that it is a continuous frame. Our sequence counter is a 1, saying that it's the first in the sequence, and then we'll fill out the rest with the data. The next message, again, is a 2, continuous, and our sequence number is a 2, indicating that it's the second in the sequence, and we'll finish sending the rest of our data, completing the 18-byte transfer. Now, let's take a look on an actual car on how to read the VIN. I'm connected to the vehicle's CAN bus with my virtual machine ready to go, and I've split my terminal into 3 parts so you can easily see what's going on. All of the 3 tools I'll be using here are installed with CAN utils, so if you don't have that yet, go ahead and get it. The first I'll be using is candump, and this will let us see every message that's going on, and we can start to understand the exchange. To do that, we first need our interface setup, which I've already brought up with the IP link command. We will use candump, can0 to specify the interface, and that'll dump all of the traffic on the bus, which we don't want. So we're going to use candump can0, and then pipe that to a grep to filter what we want. And then we want to look for 2 IDs, so we're going to use quotes. We're looking for 726 and backslash to break this pipe, and 72E. The reason we want 726 and 72E is because we know 726 will deliver the VIN, and 72E is the ARB ID that's 8 higher than the one that we're requesting. So now we can see the command is running, but we don't yet have traffic on candump for either of these ARB IDs, so we'll keep moving on. Now, to handle the isotp and all of the exchanges that we need for things like flow control, we're going to use the command isotp receive. To do that, we'll just use isotp receive -p to pad the rest of our data with zeros. So if our data is less than 8 bytes, this will expand the data to be 8 bytes and use zeros to do that. -s to specify our sending ID of 726. -d to specify our destination that we'll be listening to of 72E. -l to loop this so it doesn't exit after the first command, and specify the interface can0. So once again, this is listening, ready for a response, but we don't yet have traffic here. Now that we're ready and listening, we're going to use the isotp send command to send a request for the VIN. To do that, we're going to use echo 22 to specify the service 22, and then F190 to specify the VIN. Now alone, if we send, this will just echo the command back to the terminal, but what we can do is pipe this into another command, isotp send, -p to pad with all zeros, -s to send 726, -D to specify the destination or listening as 72E, and then can0 to specify the interface that we're sending on. And all we do now is send it. So now you can see we have a response. We have a single message requesting the data by identifier. We have a first frame. We have a flow control frame. And we have consecutive frames. So let's go take a look at what we're seeing. First, we're sending to 726 a single frame that's 3 bytes long, asking for data by identifier, and then we're identifying the data we want as the VIN number with F190. Then we receive a response on 72E that is the first frame of the sequence, and the next 3 bytes are your data length, which is hex 1B, or 27 bytes in decimal. And then it begins with the 62, which we'll remember is the 22, or the service ID, plus 40, specifying that it's sending us F190, or the VIN number. And then the rest of the data that it sends is the first 3 bytes of the VIN number. Then we respond with a flow control specified by the 3. We're saying to send all of the blocks all at once with no delay. Then it continues responding with the 21, which is to say that this is a sequential frame, first in the sequence, and then the rest of the 7 bytes in this frame are the data of the VIN. And then a 22, again indicating that it's a sequential frame, second in the sequence, and then a 23, sequential frame, third in the sequence. So this is how the VIN number is transmitted over ISOTP using UDS in your vehicle. When we come down here to see what we got with ISOTP receive, we see the first byte is a 62, which is the service ID of 22 plus 40, F190 to identify the VIN, and then the VIN number right after that. So it's as simple as that to use UDS and ISOTP to request information from an ECU. You can use things like tester present to look for ECUs that are responding indicating that they provide that service, or any other UDS command that you can find in the Wikipedia link, and we'll go into more of them in part 2 of the video. Thanks for watching.
Block Harbor. Building great solutions for automotive cybersecurity to keep mobility safe.